Hi, my name is Chloe Devine, and in this presentation, I'll review with you the machine learning electrical output of a company I've named Apex Energy Center's combined cycle power plant that uses a combination of gas turbines, steam turbines, and heat recovery steam generators to generate power. I've used a set of 9,568 hourly average ambient environment readings from sensors at the power plant, and I've compared temperature, AT, versus power output, PE, and created a model that will enable future energy output predictions. This machine learning model has been created using mean absolute error as my primary output evaluation metric because it provides a straightforward, on average measure of how far off the machine learning predictions are from the actual energy output. Included are also the R-squared metric to give a percentage-based measure of how much variance in energy output exists. Together, these two metrics provide interpretability and an average energy usage in a shareable and digestible format. The dataset includes 4 environmental variables: temperature, ambient pressure, relative humidity, and exhaust vacuum, which represents the controllable and measurable conditions under which the power plant operates. These variables directly influence the net electrical energy output and therefore serve as the features for the regression model. The target variable is the net hourly electrical energy output, which we aim to predict. Considering the algorithms covered in this course, I considered 3 algorithms for this numerical regression task. The first one, linear regression, because it's a simple baseline model for understanding linear relationships. Second, decision trees, a nonlinear model that can capture feature interactions more effectively. And third, random forests, an ensemble of decision trees that reduces variance and typically improves predictive performance. Below, you can see the environmental variable comparison between roughly the 9,000 hourly records from the Apex Energy Center combined cycle power plant. PE is a target variable we aim to predict. In these graphs, you can reflect on the power output relative to the features present in the data and their overall effect, notably temperature versus the power output, has a clear downward trend with strong energy output and exhaust vacuum as the potential output as a strong curvature, behaving non-linearly. For my validation strategy, I used a fixed validation split, which aligns with the methods covered in the course and automatically reserves a portion of the data for validation during training, allowing me to compare the performance of different models on the same validation set. I thought about using k-fold cross-validation, but I couldn't find a way to do it in Google AutoML. Google AutoML was my preferred platform for evaluating performance, so I kept the fixed validation split. I want to note that I was unable to upload the CSV data into Google AutoML, and so after trying for 2 hours with the help of Gemini and ChatGPT, the decision in the end was that Google AutoML was having an issue, that it wasn't an issue with the data at all. And so I don't know how to code in Python, but that was my next source I thought I might use. And so I turned to ChatGPT to generate the code to output my results in the graphs in this presentation. I have included screenshots of that code in the appendix, even though I switched to Python. And I stayed with the fixed validation split, feeling that this approach ensures fair and consistent model comparisons and avoids data leakage by keeping the test set separate until the final evaluation. To determine the best model, I compared 2 algorithms covered in the course. A tree-based random forest. This model captures nonlinear relationships and interactions between variables and is typically more flexible than a linear model. And linear regression, a simple interpretable baseline that models linear relationships between environmental features and the energy output. On this slide, I'm comparing the predicted versus actual power output for both models. With the random forest, the model closely follows the ideal 45-degree line. The predictions are much more tightly clustered, indicating that the model captures the underlying nonlinear relationships in the data. In contrast, linear regression shows a wider spread around the ideal fit line. This indicates that the model is underfitting because it can only capture a straight line relationship, while the real data is more complex. On this slide, I'm comparing the residual plot for both models. With the random forest, the model is evenly distributed around 0 with no visible pattern or trend, and overall it indicates a good fit with minimal bias. In contrast, the linear regression model residuals form a curved bowl pattern. Systemic error is present because it can't capture a nonlinear structure, and it indicates the presence of underfitting. Overall, random forest clearly delivers more accurate predictions. Using mean absolute error on the validation set, the results were that the random forest had 2.48 with a 96% target variable. Linear regression had 3.63 with 93% target variable. Because the random forest tree model achieved a lower mean absolute error, I selected it as my final model with a final mean absolute error of 2.33. The 4 variables chosen for this model were crucial because they were all numerical and directly related to energy production. Using the random forest algorithm enabled us to predict accurately that the temperature feature was the most influential factor in predicting energy output, aligning with thermodynamic expectations. It's clear that exhaust vacuum also plays an important role. In conclusion, this model evaluation and comparison clearly defined that linear regression could not fully capture the nonlinear patterns in the data, as shown by its curved residual pattern and lower R-squared score. The random forest model, however, produced tighter predictions, randomized residuals, and higher overall accuracy. With higher predictive accuracy, minimal residual bias, and strong alignment with real-world turbine behavior, random forest is the optimal modeling approach for the Apex Energy Center combined cycle power plant. As noted above, Google Auto Machine Learning was my preferred platform for evaluating performance because I don't know how to use code in Python and I don't use Excel as an analyst. I created a Google Auto Machine Learning account and followed the instructions to use it, but was found that I was unable to upload the CSV data provided to Google Auto ML despite 2 hours of trying with the help of Gemini and ChatGPT. It would pull in the column values, but not the features, and kept giving null values. In the end, the decision was that Google Auto ML was having an issue. I felt blocked and overwhelmed at this point. Instead of giving up, I used ChatGPT to generate code to output the results and the graphs that I wanted for this presentation. I've included screenshots of that code in the slides below. Defining data and features, defining target and applying data split, model comparison, random forest, mean absolute error, the random forest variable test run, the relationship between predictors and electrical output, training random forest, training the linear regression, calculating for the mean absolute error, and R-squared. Feature importance plot,